The archer's paradox starts with the assumption that you have to aim your arrow straight at the bullseye, but you also have to do the same for your bow because that's where where the string is going to push the arrow as it goes back to its original position. But you can't have both of these things happen at once. The solution to the archer's paradox is to simply start off with the arrow slightly aimed off to the side and then just letting go as it will just bend around the bow. This sounds kind of weird, but it just happens because the normal force of the archer's fingers would push the tail this way, and then that slight bend that would result from that would be further amplified by the force of the string coming back to its original position upon release. So basically all that a person who makes an arrow has to do is to make sure that the arrow can bend a bit. When you're choosing an arrow to buy, you can actually choose between different levels of stiffness, which is also called arrow spine. If you look at this chart here, it goes from about 700 to 250, and the higher the number is, it correlates to a less stiff arrow. This is because what they do is they get a shaft, and then they put a random amount of weight on it. It's a standard for their measuring process, and then they measure how much it deflects. And with that number, then it correlates to the number on the chart. So if you look at this chart here, you can estimate how stiff you need your arrows to be based off of your draw weight, which is going to be how strong your bow is, and then your arrow length, which is going to be dependent on how long your arms are, and then other factors such as point weight, which I'll be going into in more detail. If you want to adjust how stiff your arrow acts in flight without actually buying a new arrow, you can simply adjust the masses on each end of the arrow, the nock right here, and the point. The point is actually where most of the mass of an arrow is. It's up to 40 to 80% of the mass of the shaft in total, and so this side is going to be the heavier side, and this is what people usually adjust. What increasing the mass at the ends of the arrow does is that it makes it harder to move that part. It increases the inertia, which means that the arrow is going to bend more, so it acts as if the shaft is less stiff than it actually is. Another part of the bow that directly affects how much an arrow bends in flight is the bow plunger, which is going to be this little thing right here. What it does is that it has a spring on the inside, as it's represented by a spring in this diagram, as you can see. So what happens is that when you deflect the tail with the normal force of your fingers, then this end is going to want to move this way. But what the spring does is it counteracts that, and depending on how strong this is going to be, depending on who you are, your form, etc., then you're going to want to adjust the bow plunger to match that accordingly. So those are all the different ways that you can adjust how stiff your arrows act in flight. As you saw, there are a lot of different ways to do that. And to check if you've done it properly, what you do is you shoot a lot of bear shafts and you shoot a lot of arrows with fletchings on it. And so what happens when you put a fletching on an arrow is that instead of just going along this path, what you get is a windage force and air resistance that would push on this end of the arrow and then correct it to be a little closer to center. And so this difference is going to happen as long as your arrows are not going perfectly straight. So what you want is for your arrows to be going perfectly straight. That's how you know if your arrows are acting stiff enough. And so by doing bear shaft tuning, which is kind of a tedious process, you can figure out if you have to adjust your arrows more or not. When the arrow is too stiff for the archer, what happens is that it is angled off to the left and vice versa for when it's too weak. And so there are a lot of principles that depend on the qualities of the arrow. Its stiffness, things like its length can affect that as well. And so if we want to go into like a mathematical proof or reasoning for why that is, then we have to go into what's called the Euler-Bernoulli beam theory, which is going to be the next part. The first question that we should be asking ourselves is, why are we using this beam theory? And that has to do a lot with its core assumptions. So its first core assumption is that plane sections will remain plane. What plane means is that the entire shape is going to be able to fit in a 2D plane, and on top of that, it's going to be perpendicular to the neutral axis. And to explain what the neutral axis really is, we should look at what happens when a load is applied to a beam. When a load is applied, like this one, then the top part is going to be compressed, and the inside, the bottom side is going to be tense or tensile. Tensile forces are going to act on it. And so it has to transition from going this direction to this direction, and at some point it's going to be zero, which is going to be where the neutral axis is. So some examples of what happens when this plane sections will remain plane assumption is not met would be these two right here. this first one does not form a 90-degree angle. This one does form a 90-degree angle, but this cross-section will no longer fit in a 2D plane. This assumption physically means that there are no shear or torsional forces that are significant. Shear forces are a little more complicated, but a friction force would be an example of a shear force. It acts tangentially, like that. And then a torsional force is one that would be twisting it. And so a beam doesn't really do either of those things when a load is applied to it, which is why we have to assume that those two forces are negligible. This works out really well, especially if the length to width ratio is really high, and that is the case for an arrow, so that's why we use this theory. The second assumption is that deformed angles are small. What that means is if you have a beam like this, it's not going to do that as much as you're going to do that. This is nice because if theta is small, then sine of theta is about theta, cosine of theta is about 1, and tangent of theta is about theta. And you can see all the calculations with this chart over here. And so if your theta is 5 degrees, then it's accurate up to 3 decimal places. And then if your theta is 10 degrees, then you have up to 1.5% error, which is pretty accurate. This also means that displacement is going to be about 0 too, because this would have really high displacement, this would have a very small displacement. To go into actually deriving the Euler-Bernoulli beam theory, we first have to do some basic stuff with the beams. The first thing we're going to look at is the relationship between the load, the shear force, and the bending moment. We're going to be looking at a simply supported beam supported by these triangles that has a uniformly distributed load on top of it. And so we have the 2 points A and B, which are going to be the section that we're looking at, and the distance between them is going to be d of x, which is going to be infinitely small. But even though that is infinitely small, the difference between the load on the section from point X, which is right here, to A, is going to be smaller than the load on the points on the section between the points X and B. And so that comes into play later right here when we look at that specific section in more detail. We still have that load on top, and we have a shear force on each side and the bending moment on each side. But on the right side, it's going to be a little bigger, hence these right here, because of the additional load put on that section. But we also know that the element is in equilibrium. What that means is that if we sum all the forces or we sum all the bending moments, then it's going to be equal to 0. So we take advantage of that right here with the sum of the forces in the y direction, and you simplify that and you get this relationship. You do the same with the bending moments, and then you get this relationship right here. And then when you put them all together, you get this equation, which we're going to use again later. The next part of this would be to look at curvature, and the first step in that is to look at a geometric statement. First, we're going to look at a beam that is at rest. There's no deflection in it. We're going to have we're going to have some point A with that is a distance y from the neutral axis. And then once it is deflected, which is this whole diagram over here, we're going to have an angle between where the plane used to be and where it is now. And there's like an angle of deflection right here. Then we're also going to be looking at delta, which is going to be the actual displacement of point A. The next thing that we're going to do is we're going to be looking at curvature and then using that to determine a relationship between theta and b of x, which is deflection. One thing about curvature is that the derivative of theta in terms of s is equal to curvature, but you can also plug in v of x into that formula that we all know on this side. Then, because we know that the angle of deflection is small, then we know that the amount of deflection is going to be small, and the change in deflection will also probably be small as well. So we can ignore this part because it will be negligible compared to this one. We can simplify that to this, take the integral of both sides of the equation, and take this relationship. Once we have that, we can go back to this side where I've blown up a section with the displacement of point A. Then we know that tangent of theta is going to be equal to the negative of theta over y, because the negative is because the displacement is going to be in that opposite direction. And then we know from our assumption that theta is small, that tangent of theta is going to be equal to theta, and then with that we have this equation right here. The next part of this derivation is going to be focusing on a kinematic equation that's probably new to you, but it's really simple. This right here, epsilon, is going to be equivalent to the x-direction normal strain, and that is equal to the gradient of displacement, which is basically the derivative of delta in terms of x. We plug in what we know from here, we take the derivative of both sides to it, and we just plug it in right here. And to check this relationship in terms of what it physically means, we can plug in and compare it to what we know the strains are at different values of y, or whether it is above or below the neutral axis. So when it's at the neutral axis, where y equals 0, then we know that epsilon is going to be equal to 0 as well, which makes sense because there's going to be no strain on the center of at that axis. Then if we look at where it is compressive or tensile, we know that when y is positive, right, when this above section right here, we know that the forces, the strain is going to be compressive above the axis, which makes sense, and that also is true for this equation. When y is positive, then the strain is going to be negative, which is compressive. And vice versa is true for tensile forces. Also, when we're looking at what the actual physical meaning of the second derivative of the deflection function in terms of x is, then we get that it is equal to the spatial rate of the change of the slope of the beam deflection curve. And so this basically means curvature. So that all makes sense. Next part, we're going to be looking at Hooke's law. We know it to apply to springs, but it also applies to bars and beams as well. The equation looks a little different. It focuses more on tensile stress instead of a spring force, but there still is a K value or a modulus of elasticity for a beam. It's just dependent on the properties of the bar and the material that it's made out of, and that is multiplied by the normal strain, or x, which is like analogous to x in the original function. And then we can plug in what we know to be equivalent to that from this relationship right here, and then we get this function. To check for its physical meaning once again, the tensile stress increases as y increases. Basically, once you get farther away from the center of the beam, then you experience more stress, which makes sense. The next part and the final part is to look at equilibrium. The first assumption is that, or the first thing that we know is that when you apply load, you're not applying it axially or from the x direction, you're applying it top down. And that means that total axial stresses, which is like sigma, must be 0. And so you sum the forces, they're equal to 0, and the equation for force in terms of axial stress is going to be force is equal to the derivative of the axial stress in terms of the area, the cross-sectional area, which is A. And we plug in what we already know to equal the axial stress, and we know that this section right here can be whatever it wants to be, so in order for this to be true, this equation to be true, we know that the integral of y in terms of the area is going to be equal to 0. We use this in this next part. If we want to find the equation for the distance from the neutral axis to the centroid of A, which is a cross-sectional area once again, you're going to have to plug it into this equation. And we know that this section right here is equal to 0, so everything is equal to 0. What that means in a physical sense is that the neutral axis passes through the centroid of the cross-sectional area. This makes sense because if you look at the stresses increase linearly. The magnitude of the stresses increases linearly at the same rate and is dependent on y, as you can see from these arrows. One thing to note though is that this on the top here, it's going to be a compressive force, if you remember from the beam diagram from earlier, and the bottom part here is going to be a tensile force, right, because it's bending, yeah. So if you just leave those things as it is, it looks like it would rotate, the beam would rotate, but that's not actually anything that happens. The beam doesn't really rotate like that, and that is because there's a moment of bending that balances that out. so that the total net moment is going to equal 0. So this m right here, this bending moment, is going to be added to the moment caused by the axial stresses, and that is going to equal 0. And so we plug in what we know to be, we plug in the values that we know for the equations that we found earlier, and then we can simplify out to this step. And we know that this part is actually equal to the equation for the second moment of inertia of a rectangular shaped object. And so we can replace that with the variable I. Then we get to this step, and then we can solve for the second derivative of the vertical displacement, or the deflection, in terms of x, and get this equation right here. The next part of this is to look at everything and just put it all together. This is from the first part that we did, the second part, and if you put them together, you get this, which is also the Euler-Bernoulli beam theory. If you look at it specifically to arrows or tubes, then the equation for the second moment of inertia is actually dependent on the inner versus the outer diameter of the tube. And so one way to adjust arrow spine would be to change the radius and make it smaller, or to reduce the amount of materials that you want. This is something that they've actually done. If you compare the ACE arrow to the X10 arrow side by side, the X10 arrow, which is the newer one, is a little thinner, and they are able to reduce the radius, which then reduces the effect of wind on the arrow, while keeping the second moment of inertia the same, because they're able to adjust the difference between the inner and the outer radius. The next part would be to look at the vibration of the arrow, and in order to do that, which is to find the dynamic beam equation, we have to examine this functional S. To break apart what's in it, we have the kinetic energy of the arrow, then we have the potential energy due to internal forces, which is where the Euler-Bernoulli beam theory that we talked about earlier is going to come into play, because for that we talked about internal bending moments and the internal axial forces. Then right here we have the potential energy due to a load that could be applied. In this case, we don't have a load that's continually applied, but because we're going to be looking at the general form of this equation first, that's just going to be there. To find the dynamic beam equation from this functional, we have to find what's called the Euler-Lagrange equation from the functional S, and what that does is it determines a functional that minimizes the functional S. The details of that are kind of out of the scope of this class, so I'm just going to skip over it. But the solution that we get is this function right here. And then for an arrow specifically, there is no support and there's no continually applied load. That gives us specific boundary conditions. If you look here, that there's like a point on the arrow that doesn't really get displaced that much. And so with that, we can figure out that the derivatives of the function of displacement at those points are going to be 0. And with that, we can simplify, we can try to find a solution to this equation right here. First, we can simplify down a little bit. On this side, we know that the flexural rigidity is the same, is constant, because the beam is made out of a homogeneous material and a constant cross-section. So what that basically means is that at each cross-section, the elastic modulus and the second moment of inertia is going to be the same. And then with that, we can simplify the left side to this. Then we also know that this is going to be equal to 0 because an arrow doesn't have a continually applied load to it as it's flying out. So we have this equation. And then the solution for this equation is the general form is that we can use we can figure out things such as K and A depending on each specific situation. And for a free beam that is unloaded, then we get this right here. We can relate the frequency to the rigidity constant and also the mass per unit length and the wave number. But this one isn't as accurate in the situation that we're looking for because it doesn't take into account that an arrow might have multiple different natural frequencies, which is what the eigenvalue takes care of. And then what we get is a clear relationship between the frequency, and other factors such as the rigidity constant, the mass per unit length, and the actual length of the arrow. The reason why we are going to be looking at that and why that's important at all is because we want to look at what's called the clearance frequency. And right here we can see that what we want is this cycle right here, 1.25 cycles, to coincide with when the back end of the arrow is close to the bow. And what this does is it flexes it in a way that makes this part farthest away from the bow at that point. And the reason why that's important is because it minimizes the chances of the arrow hitting the bow on its way out and affecting its flight. And so if we want to maximize that, then that's basically part of what we're doing tuning for. And so we want to be able to calculate that based off of the properties of the arrow. But to actually calculate the clearance frequency, we can use energy balance instead of this equation over here. This one might be more useful for someone who's manufacturing an arrow because a lot of these things are parts of an arrow that we can't really adjust after buying the arrow. But if we want to calculate the clearance frequency experimentally, kind of in your own backyard, then we can just use energy balance. We have the equation for the kinetic energy on this side, and then what they did was they figured out the work done by the bow on this side. They figured that the efficiency of energy transfer is going to be about 90% from the bow to the arrow. Then they used the displacement of the string when drawn, which is going to be this right here, and also the force of the bow, or the draw weight. With that, they found the final horizontal velocity, which is going to be constant throughout because there's no horizontal acceleration after the arrow leaves the bow. What we can also do is treat it like a spring. If you remember from the derivation earlier, we did use some parts of Hooke's law, and so it does hold true that you can treat a beam kind of like a spring. So with that, what we did was the K value, instead of just using like a K value, we used the force times or divided by the displacement of the string when drawn, which acts like a spring constant for the bow, and then we just plugged it in with the efficiency of 90% in there as well. Then we know that the neutral position of an arrow is going to be at 0.25 cycles because it first starts out being flexed like that. And then it's going to become more of like a neutral position like that. And then with that, we can find the time that it's going to be at, which is going to be pi over 2 times this right here. Then after that point, then the arrow will continue forward at the v of f that we calculated earlier. So the time is going to be equal to t0 plus the distance from the string's original position to the bow, which is called the brace height, and then the distance from the tail to the rear node. We divided that by the velocity. That's going to be v of f. Then we want to find time t2, which is the time for the arrow to pass the bow. That's going to be this right here, and with that we know that the frequency that we want for maximum tail clearance is going to be 1.25 divided by t of 2, t2. And so with this, they actually calculated and predicted what those frequencies were going to be with 2 different types of arrows. And so these are all like the information for that. But what they figured out was that it would have a clearance frequency of 66 hertz, but the maximum would be 72. They predicted it would be 78. And this is what it would ideally be. And when they actually did the experiment, they found out that the actual measured frequencies were pretty accurate. So in summary of everything that is covered in this video, we looked at a pretty common beam theory and applied it to figure out the relationships between the properties of an arrow and how it moves through space while it is being shot. The theory itself looks at the relationship between load and these properties, but if we want to look at it in terms of what might be useful, we looked at the relationship between the deflection in a beam to its properties, such as the modulus of elasticity, the second moment of inertia, and the total bending moment, internal bending moment. And we know that the second moment of inertia is dependent on the difference between the outer and the inner radius. So those are the factors that might be considered when designing a new arrow. And the next thing that we looked at was the relationship between the frequency of a vibration in the arrow while it's in flight and other factors such as the length of the arrow, once again the flexural rigidity constant, and the mass per unit length. Then finally we looked at how we can equate the oscillations in a beam or an arrow and equate them to the oscillations in a spring with a mass attached to it with this equation right here. So if we want to find the actual maximum clearance frequency that we want and equate it to other properties of the bow, then we can use that equation at the bottom.